We are Team 26037, and our project is the development of a non-balloon internal retention mechanism for gastrostomy tubes. We are sponsored by Spectrum Plastics. The team will introduce themselves throughout this video.
This is our project poster, which serves as an overview of our project and will be further explored here.
Hi there, my name is Ethan Taylor, and I'm the team lead for this project. Here we work with gastrostomy tubes, or as we refer to them, G-tubes, and they're typically used for the administration of fluids or medication to those who are unable to eat or swallow safely. Implanting these is a fairly common procedure occurring roughly 160 to 200,000 times per year, and here at the office, we work to make them better.
Hi, I'm Jesse, a biomedical engineer and the procurement lead for this project. The key objective here is to not use air or water for the expansion mechanism, since the current balloon model has a failure mode of bursting and leaking.
I'm Dan, also a BME, and we want to keep patient comfort in mind, so my focus is on safety and risk management.
My name is Luke, and I'm in material science engineering. Spectrum is a silicon-based site, so the anchor will be fully made out of biocompatible material.
I'm Ashton, another BME, and the key medical device standards that we'll be adhering to for this project are ISO 20695, ISO 10993, ASTM 2528-06, and ISO 80339-3.
And I'm Carly, a mechanical engineer. Overall, the main goal of the project is to provide a reliable anchoring mechanism that minimizes the risk of dislodgement.
In order to address this goal, the team has modeled a retention mechanism off of a drywall anchor. This allows the device to shrink enough to fit easily through the patient's stoma, while providing a stronghold when expanded that prevents accidental removal. These videos depict multiple iterations as the team continued to narrow down which performed the best. An insertion rod has been designed in conjunction to fit through the external component of the G-tube, trifunnel, which is what stretches the anchor to collapse for insertion and removal.
Our main focus is the retention capabilities of our device. The more material, the more force it can withstand when being pulled out of the stoma. The insertion rod should be the only thing to collapse it, with its T-shaped handle, design mimicking other clinical accessories. We incorporated the original balloon in the middle, which provides a continuous feeding lumen and provides additional elasticity within the mechanism. The distal tip and base junction provides adequate bond area between the balloon and are designed for more durability and long-time use.
While a majority of the project focuses on the internal retention mechanism anchor, here's a system architecture that further defines each system and subsystem the team also integrates into the medical device. Each of these components will be present in the final design and available to view on design day on May 4th. The system block diagram here demonstrates how each of these subsystems interacts with one another, and most importantly, how a customer will use the system. During implant and removal, the user interacts with the insertion rod to collapse the anchor, and during average daily living, the user interacts with the feeding ports for nutritional or medicinal purposes.
This slide breaks down more specifically how each component is laid out in the device and how they combine to make a G-tube per implant. This point design emerged as the version that best balanced the requirements of the system. This can then be evaluated against the project's functional requirements and used as the basis for the final prototype.
Now that each part has been defined, let's go into how we made this happen. The manufacturing process for our prototypes took 3 distinct locations, the first being Aztec. Here, we worked on injection molding with water-dissolvable molds. These were helpful because it allowed us to make prototypes without having to worry about core pin removal. Our second location is HSD. Here at Health Sciences Design, which is right below where we just were, we use their silicone resin printer. This has allowed us to do rapid prototyping, printing as much as 10 prototypes at a time. And here we're at our final site at Spectrum Plastics. Here we take our core balloon and put it into our anchor prototype. Our final prototypes, we have 2 different versions. The first is 40A silicone and it's SLA printed at HSD. The second is 70A silicone, which is cast molded, and we do that here at Spectrum. We then take these prototypes and put them against our system requirements.
The anchor must withstand an external force of 15 newtons. The anchor must also allow for at least 9 milliliters per minute to flow through it, although we are more so aiming for 400 milliliters per minute to mimic the current device. The mechanism must shrink to 22 French to fit within the stoma during implant and removal, so as to not exceed 4 French over our 18 French tube. To measure durability, it must collapse more than 20 times without breaking the rod or the anchor. For patient safety, the outer diameter of the anchor, when expanded, must not exceed 1 inch. And lastly, for ease of manufacturing, the design should seek to minimize the number of mold blocks to no more than 5.
The overall design process for this project was very cyclical. It started with an initial design and moved into 3 main analyses which informed changes to the design. A substantial amount of effort was also put towards risk assessment and mitigation as we approached our final product.
I performed a computational fluid dynamics analysis in order to assess the flow rate through various models of the anchor. The results between the models of the CFD match the performance ratio of the actual physical models, demonstrating the importance of this analysis.
My role focused on performing a finite element analysis to simulate the expected forces on the insertion rod and anchor. This helped determine what material to use for the rod, which was ABS based on simulation results, and provide expected areas of high stress on the retention mechanism.
My analysis aided in predicting where the anchor is most vulnerable to breaking at the distal or proximal end. This aided in design reinforcements and risk mitigation.
This failure modes and effects analysis was adjusted throughout the project to evaluate likelihood, severity, and detectability of failure modes to help adjust the mechanism design. The most notable design change that came from this was increasing the bonding area between the outer shell and the internal balloon, so the anchor was less likely to detach and fall into the patient's stomach.
Understanding the goals and our system requirements and coupling that with our analyses is what allowed us to come up with our final prototype. After performing our final acceptance test, we came up with values of 15.83 newtons for our retention, a flow rate of 566.7 milliliters per minute, and a collapsing value down to 22 French. The insertion rod was also able to collapse the device more than 20 times without breaking the mechanism. The margins are presented here.
Considering challenges during the project, every prototype on this table represents a tactical response to failure. One iteration improved collapse for insertion, another improved retention, and another survived better than the last.
One complete use cycle for this device starts with surgical implant. The device will come pre-packaged with the insertion rod. All a physician has to do is insert the rod through the trifunnel, collapse the anchor, insert the G-tube through the stoma, and remove the insertion rod. The external bolster can be adjusted for patient comfort, and the device is ready for feeding or medicinal purposes. This overall demonstrates our final deliverable to the sponsor. Only the key system requirements were mentioned before, but these tables give a complete breakdown of what the necessary performance indications were for the project, as well as what margin the device passes by. As seen in the right-hand column, each verification test passes and meets an acceptable margin of safety for device use. Ultimately, this table and these passes are what allow us to confidently say that the project has been successful.
As the project moves forward and we continue to approach design day, the main consideration for future iterations of the device hinges on the development of an aluminum mold block. This is what allows for high temperature injection molding, which is how Spectrum typically mass produces their products.
All right, so to recap what we accomplished this year, we took a ballooning G-tube and repurposed it into a mechanism that doesn't inflate.
Instead, we use an insertion rod to collapse that new mechanism for insertion or removal. Once the insertion rod is removed, the anchor expands and sits within the patient.
It is biocompatible and designed for ease of manufacturing and mass production.
And our device improves on safety by eliminating a major failure mode, all the while adhering to the same standards set by current ballooning G-tubes.
We also just want to say thank you to our sponsors and our mentors throughout this project.
Your insight and aid has been so helpful in helping us create a functioning final product.
Thanks!